Okay, so thanks, Russell. So thank you all for coming. And let me just say a few words about the upcoming boot camp. Today, I'm going to give 3 lectures, go back to San Diego, because I got to complete this program, summer program. And in the next 4 days, so the last talk of today will be given by Thor Husfeldt, who will talk about the exact algorithms for NP-complete problems. And subsequently, Russell will talk about de-randomization. Ryan will talk about connections between satisfiability and circuit lower bounds. And Virginia will talk about complexity theory of P, and especially to the emerging complexity theory of P. And finally, Daniel Marks will talk about parameterized complexity. So we have a full schedule, 4 talks a day for 5 days, for 5 days of the week. So, okay, so I changed the title, not the contents of the talk. The talk was titled as Satisfiability Algorithms 1 and 2, but if you think about it, it's the combinatorial properties of the KCNF that are central to both lower bounds and upper bounds in this area, and I want to take a look at some of the key properties of KCNF that led to various interesting results, and those are the first 2 talks. Okay. And I would like to thank my co-authors, Russell, Mike Sachs, Paul Pudlak, and our students, Francis Zane, Chris Calabro, William Matthews, and the future students, and the current students. Okay. So that's overview of the talk, and those are the 3 combinatorial properties I will talk about, and talk about the consequences. And some of the talk will mostly focus on intuition. Towards the very end, I'll become more and more sketchier, but the first 2 parts, I hope to give you a very good sense about the ideas and applications. So what's the general motivation? So it's about satisfiability problem, and the general motivation is faster algorithms for SAT solvers, for example. Okay. But more importantly, we want to understand the structure of the KCNF, and which might explain, which in turns out kind of explains the complexity of many other problems, and also the lower bounds. Okay. So these are the general motivation, and so let me give you a much more specific motivation for this talk. My foray into satisfiability algorithms is motivated by depth 3 circuit lower bounds, and in particular, so the motivation is, so this is after this is post Hustard's lemma, where one has proved very strong exponential time lower bounds for parity function for constant depth AC0 circuits. And so the goal here is to prove even stronger lower bounds. And so that's a kind of that's a technical goal, and I will show you how it is motivated by other more sophisticated circuit models. So we have these depth 3 circuits. So you had the top level you have an OR gate followed by a bunch of AND gates at the second level, and at the bottom level you have OR gates. Okay. And we also specialize these circuits when we restrict the fan-in at the bottom to be K, and then we call them as sigma pi sigma sub K circuits. Okay. So this is the circuit model, and our motivation is to prove strong lower bounds. So what's known so far? Okay, prior to 1997. Okay, and so switching lemma tells us that parity requires 2 to the c times square root n size for computing. Okay, where c is strictly less than 1. And subsequently, Pavel and Mohan improved that lower bound using a top-down technique, which is only applicable for depth 3 circuits. It's not clear how to apply it to depth 4 circuits, to get a slightly better lower bound of 2 to the 0.687 times square root n for parity. But on the other hand, parity, so the best known upper bounds are of the form 4th root of n times 2 to the square root n for depth 3 circuits, and with a bottom fan-in of square root n. Okay. So one concrete motivation is that can we reduce the gap between lower and upper bounds for parity for depth 3 circuits. So the talk will focus on this very technical and interesting question and see what progress we can make. So let me give you one more motivation for depth 3 circuit lower bounds. If you look at larger circuit models like linear size log depth, and it turns out they can be decomposed into, so they can be written as depth 3 circuits with a large fan-in at the top level and somewhat small fan-in at the bottom level. So in particular, CN size D log and depth circuits can be written as 2 to the little of n size depth 3 circuits, where the bottom fan-in is bounded by n to the little of 1. Okay. So even more, if you restrict the circuits even further to make them series parallel, so you can get a somewhat more simpler circuit. So for example, so there's a trade-off between the bottom fan-in and the top fan-in, and so the trade-off behaves in that fashion. So the difference between the previous and this result is that so the fan-in could be constant at the bottom level, and so you have to pay somewhat higher penalty, so you have to have a higher fan-in for the top gate. So similarly, you can take NC1 circuits and decompose them into depth D circuits, and the size behaves. The fan-in and the size are related in that fashion. Okay. So the point here is that if you take more standard circuit models, they can be decomposed into, so they can be written as small depth circuits with very, very large size. Okay, so that's an important point. And so one way to think about it is that by large, I mean for depth 3 circuits, you can look at the following quantity. Take the log of the top gate fan-in, take the bottom gate fan-in, take the product. The product is typically a 1 or more. So those are the kind of circuits we're looking at. For parity, that it achieves exactly 1. For all these other circuit models, the product is much larger than 1. But whereas if you look at the switching lemma proofs, it was only able to prove lower bounds for circuits where the product is less than 1. So once again, it's the cutoff point is that the product of the bottom fan-in times the log of the top gate fan-in. So the goal here is that can we break through that barrier and prove stronger lower bounds where the product is greater?
If the product is n?
Product is n. So as a fraction of n, it's 1. Yeah, right. Okay, so let's take a somewhat more concrete. So this is basically the goal. So can we prove tight lower bounds for parity, or can we prove lower bounds that exceed this trade-off between the bottom fan-in and the top fan-in? So I will now we'll go to the circuit. We'll go to the satisfiability problem, and I will introduce the satisfiability problem and try to connect these two problems. Okay. Pardon me? So when k is square root n, so 2 to the square root n is the cutoff point. So we are given a formula or a circuit, and you want to check it is satisfiable. And so the examples are KCNF, CNF, and formulas, and AC0 circuit and C1 circuit, poly-size circuit. So this is the general satisfiability problem, and we know that we can decide this in time the size of the formula times 2 to the n by doing exhaustive search. And the goal is to see whether we can improve upon this exhaustive search. Can we obtain savings over the brute force method? And one way to express the complexity is the size of the formula times 2 to the n times some factor. That factor, let's call it 1 minus mu, and mu is the savings that we can get over the exhaustive search. Okay. So we are specifically interested in the class of KCNF circuits, and it turns out better satisfiability algorithms for these problems or seem to be connected with lower bounds and also seem, and more importantly, combinatorial properties of KCNF seem to be related to both lower and upper bounds. So the best known prior to 1997 is, so the satisfiability savings is 1 in 2 to the k. So you take each class, try out all possible settings, and then you develop the DPLL tree and then show that you can get a savings. Okay, so let me now quickly show you the connection between the KCNF properties and lower bounds. So this is inspired by the top-down approach of Mohan and Powell, and where they try to improve the parity lower bounds by using a top-down approach, and we use a somewhat similar approach. So let's take a circuit, sigma pi sigma k circuit, with a top fan in S. Okay. And let's focus on the parity function for now, and this circuit computes a parity function. Let's assume that. So, and it turns out by simple argument, so one of the subcircuits, which is a KCNF, must accept at least 2 to the n over s many inputs of odd parity and reject all inputs of even parity. The top gate is an OR gate, so therefore the bottom gates are doing much of the computation, much of the filtering out of even inputs. And the top gate is summing up all the, taking the union of all the efforts of the KCNFs. Okay. All the KCNFs together must account for all inputs of odd parity, and each one of the KCNFs must reject even inputs. So that's the kind of constraint we have in the circuit. So therefore, we can say one of the circuits must accept at least that many inputs. So the top-down argument goes like this. So if we understand KCNFs well enough, maybe we can argue that a KCNF cannot accept too many inputs of odd parity while rejecting all inputs of even parity. Okay. So that's the strategy. And so what do we know about KCNFs? Okay. So that's where we begin. So this is where we started our question, Powell, and we started thinking about what do we know about KCNFs to obtain strong lower bounds. Okay, so the starting point is the following thing. So if you look at a KCNF with the previous property that it is accepting some odd inputs while rejecting all even inputs, so you can look at all the inputs that it is accepting or satisfying. And they are such that those satisfying assignments are isolated. So that means if you flip one of the bits, then you get an assignment which is rejected by the KCNF because it's an even input. Okay. So we call such solutions isolated if the Hamming distance. So within Hamming distance, if you flip one of the bits, so the corresponding assignment is a false assignment. Okay. So what we are asking is that what is the maximum number of isolated solutions that a KCNF has? So this is a somewhat general question. If we can get a tight bound on this, then we can get a tight lower bound for parity. So by using the top-down argument. Okay. So we show that this number is actually precisely 2 to the n times 1 minus 1 over k. So if you look at the block parity circuit for constructing parity with depth for depth 3 circuits, they achieve this bound. And so how do we prove that? And so once we prove that, so then we will be able to show that sigma pi sigma k circuits with bottom fan in k must necessarily need 2 to the n over k KCNFs to compute parity. So each KCNF can accept that many odd inputs, and together we need 2 to the n over k. So if you look at the product of the log of the top fan in, which is n over k, times k, so that's n. If you take it as a fraction of n, so that's it's 1, and that's basically where this bound meets. Okay. So let me show you how we can show such a property, and it's obviously that so the nice thing in computer science is that when we can prove properties by means of algorithms. Okay. So we'll come up with an algorithm that shows that the number of isolated solutions cannot be too large. So one property of the KCNF when you have an isolated solution is the following thing. So fix any isolated solution. So let's call it X. Okay. So look at plug in the values of this assignment X into the formula. So look at each class. Some classes turn out to be minimally satisfiable. Since it's a satisfying assignment, so every clause is satisfied. And not only that, some clauses are minimally satisfied. By that I mean there are some clauses where all the literals except 1 are 0. And it turns out, so we call such clauses critical clauses for this assignment X. And it's not only that for each variable there must be a critical clause at this assignment. So when you have an isolated solution, for each variable you have at least one critical clause, and all the critical clauses are distinct. So if you were to flip that variable, so if there is no critical clause, if you were to flip that variable, so the formula must become false, and the only way it can become false is that there exists a clause where this variable is solely true, or the corresponding literal is solely true. Okay. So we first make this simple observation that there must be at least one critical clause for each variable at a satisfying assignment which is isolated. So what we are going to do is that so we are going to take advantage of the critical clauses to compress the solution. So we have a shorter code for the solution, for this isolated solution, so given that we have critical clauses. So the idea is that if you know that all of them are 0, but for 1, so you can guess somehow if you know the other variables and their values, then you know this variable must be 1, and then you can determine its value. So this is like the unit clause heuristic. Okay. So to put this into practice, so what we are going to do is that we take a KCNF, we take a permutation. So let's fix an isolated solution. Okay. And so we use the following algorithm to compress the solution X. So we fix a permutation, and so we look at the next bit according to the permutation. If there is a clause that contains this variable as a unit clause, so that means if there is a clause that only contains this variable, then we know that that variable must be set to 1. So we set that variable. So rather than setting the variable, we simply delete that particular variable from the satisfying assignment. So we are going to get rid of some of the bits from X based on this permutation, and the resulting string is the compressed string. So the idea is that we're going to show that this is a one-to-one function. We can recover the string X from the compressed string. So let me show you the recovery algorithm. And
sorry, does the representation need to contain, or do you need to express which clauses are the critical clauses? Because isn't it possible some of them aren't critical?
So we are given the solution X, okay, and we are given a permutation. So we go through each bit in that order, and if that bit is not needed, and if that bit position, and if the bit value is implied by the formula, then we delete that bit.
You mean the critical clause for that bit, or any critical clause containing that one?
It's any critical clause, yeah, that contains that one.
But then
we don't need to know what the critical.
This is to create a compressed representation, right? So don't you need to know which clauses are the critical clauses in order to get
Right.
the representation back.
So right, so we're given the input x. So therefore we know what the critical clauses are.
So I think he's asking, how do you know if there's a critical clause containing X? And the way you know it is by that point, since we're looking for critical clauses where all the other variables have already appeared, that means all the other variables will have been set to false. And so that clause, when simplified, at that point will just be X itself.
But you need to know that that's a critical clause.
But we're saying
That is self-evident. So that means when it becomes only a unit clause,
Yeah, every time it becomes size 1, that is a critical clause. There might be,
if it, yeah.
so what I'm doing is that I'm mapping, okay, remember I have the input x. Okay, and we know it's a satisfying solution, we know it is isolated solution. So there will be critical clauses for that input. So the only issue is that which bits of x are redundant given the formula and given the permutation. So that we can determine given we map this x to the compressed x by going through the bits in that order and figuring out which bits are implied, and critical clauses are the ones that will help us in this regard. So we have all the knowledge here. So this is right. So then I will show you how to recover x given this compressed string. So of course we need to know the permutation. So the permutation is given and the formula is given and the compressed string is given. So then I will show you how to recover. So that kind of shows given the permutation and the formula, we have a one-to-one mapping between the isolated solutions and compressed strings. So this is what I do. I'll start with the formula. Okay. And and if the formula has a unit clause, then I know for the formula to be true, that unit clause must be set to 1. So therefore, I set to 1. Okay, sorry. I'm going to look at the variables in that order. And if the next variable has a unit clause in the restricted formula, so then I'm going to set that variable to the appropriate value. And if there is no such unit clause, then I take the bit from the compressed string, then I will set that bit. So the idea is that, so the permutation is telling me, so I'm going to give you an explanation in a second to see why and how often this is going to work. So either the bit is implied, in which case I can deduce it from the formula, or if the bit is not implied, I will take it from the compressed string. Okay, and so then I recover x. It's basically the reverse process, and it's a one-to-one mapping. So the main issue is that what can we say about the length of the compressed string? So what the satisfiability coding lemma says is that fix any isolated solution. So if you take a random permutation, so the average compressed length is basically 1 minus 1 over k fraction of the total length. So the argument is the following thing. It's a very simple argument, one line proof. And so if you take the satisfying assignment x, which is isolated. So therefore, it has a critical clause for each variable. Okay. So if you take a random and fix a variable I, and if you take a random permutation, the probability that variable appears after all the corresponding variables in its critical clause is 1 in k. So each clause has length k. And look at the corresponding critical clause for the variable I, and of the k variables there are, so the critical variable is likely to appear to be the last variable among them with probability 1 in k. So therefore, with probability 1 in k, so this particular variable can be compressed or can be deleted from the string. So therefore, the total average savings is n times 1 minus 1 over. So the total savings is 1 in k fraction. So from this it easily follows. So there exists. So there are at most 2 to the n times 1 minus 1 over k solutions which are isolated, and so we know that average compressed length is at most n minus n over k, and we know, so therefore there exists one permutation such that the average over all isolated solutions is still n times n minus k. So the point is that for a particular permutation and for a particular isolation solution might be compressed, but for some other solution it may not be compressed. So we reverse the quantifiers and we show that there exists basically one so there's at least one permutation that has average length over all isolated solutions. Okay. So by using a simple argument, so we have a kind of coding argument that prefix-free encoding argument that shows that the number of solutions. So what we have shown is that there is a permutation that maps isolated solutions to compressed strings, such that the average length is 1 minus 1 over k times n, and so then we can use the fact to argue that the total number of solutions is at most 2 to the n times 1 over k. So that's basically the satisfiability coding lemma, and so from that, so we conclude that sigma pi sigma k circuits, if the bottom fan-in is bounded by k, so then parity takes 2 to the n over k size, precise. So you want to extend it, so the sigma pi sigma k model has the restriction that the fan-in is bounded by k. So you want to extend it to include arbitrary circuits, and what we show is that when there's no restriction on the bottom fan-in, okay, the depth 3 circuits must take 4th root of n times 2 to the square root n size. So this is basically up to constant factor. So even the constant factor is off by a 2 or 4. Okay. So this is the lower bound for computing parity, which meets the upper bound within a small factor. So to go from restricted circuits to a more general bottom fan-in circuits, so we have to look at we have to generalize the notion of isolated circuits, and so use a weighted argument. I will go through that in a second, and so the problem is that the previous argument says that when the clause lengths are uniform, so you have 1 in k chance that a variable, so that a particular variable becomes unit class. Okay. Now the clause lengths are varied. So if you take general depth 3 circuits, clause lengths are varied. Some may have large clause lengths, some may be very short, and you want to kind of argue over all these things. So let me quickly generalize, and we do know for every solution there are critical clauses for every variable. Okay. So let's look at the number of. So let's group the critical clauses by their length. Okay. Let's use this quantities n sub l of x to be the number of critical clauses of length L. So we know that the sum of the critical clauses should be equal to n, because there is 1 for each variable, and we define the weight to be 1 over the inverse of the length. 1 over the length of the critical clauses. So you basically so this is going to be the weight, and previously our weight is n over k. Okay, now this is whatever it is. Yeah.
So there could be more than one critical clause per variable, so you just pick one.
Yeah, pick one, and make the argument. So we will see in a few slides how we can exploit the existence of more than one critical clause. Okay. So we're going to make a twofold argument. So first of all, that so there cannot be too many solutions with weight greater than a particular number. The same argument as before, we are generalizing it. Before mu was n over k, now mu is whatever it is, and we are going to fix an appropriate mu in a second and kind of generalize the previous argument that you cannot have too many isolated solutions. Okay. So let's make the argument. Okay, so so we have a depth 3 circuit that computes parity. So therefore, it's accepting 2 to the n minus 1 odd inputs while rejecting all other inputs. And so for each input, there must exist a there must exist a CNF that accepts it because of the top-down argument. And so we look at the weight of that input, that particular assignment x. So we're going to choose mu to be square root n plus log n over 4. So that's where the fourth root n is going to come. So we're going to balance between those inputs. So those isolated solutions that have short critical clauses versus those that have long critical clauses. So the point is that if you have a short critical clause, okay, you cannot accept too many isolated solutions. But on the other hand, if you have long critical clauses, that critical clause can only be critical for so many of the isolated solutions. So the problem is that for a particular input, we can argue that you need to have one critical clause for each variable. But the same critical clause might work for many other inputs, or for many other odd inputs. So we're going to argue if a clause is too long, if a critical clause is too long, it cannot be critical for too many of the inputs of odd length. So that's the balance we are trying to draw between the two things. Okay. So mu is the cutoff point. So we look at the inputs. Okay, we look at the solutions or the satisfying assignments of this depth 3 circuits, a circuit with weight at least mu, and the rest. Okay. So we know that so we focus on the large weight inputs. So that's a set of S1, and we know that each KCNF can only accept 2 to the n minus mu of such inputs. So therefore, to accept all the inputs in S1, so we need at least that many KCNFs. So if you have fewer of them, so then we can't capture all those inputs in S1. So then we make the argument. So those inputs that have low weight, they can only accept many so many so long critical clauses can only be critical for so many inputs. So that's what I meant to say, and so that's so for something to be a critical clause, you need to select one of the variables. That is going to be the true variable or true literal, and the remaining are all 0. So there's so many ways you can make that happen. So therefore, that is L times 2 to the n minus L solution variable pairs can be handled by a long critical clause. Okay. So we get this quantity that for each of the inputs. For each of the isolated solutions with a small weight, so we need that many clauses at the bottom level. So the total size is going to be the sum of the KCNFs plus the sum of the bottom level gates. So you can have a lot of bottom level gates, thereby reduce the number of KCNFs. But then bottom level gates, when they are wide, they cannot accept too many inputs. Or they cannot act as critical clauses for too many inputs. So we balance these two things, and so we get the desired. So that gives us precisely fourth root of n times 2 to the square root n lower bound for parity function. Okay, so that's the lower bound coming from the satisfiability coding lemma, and we can turn this into a satisfiability algorithm very quickly. So this is how the satisfiability algorithm works, PPZ, which is we take the formula and we take a random assignment, and if there's a unit clause, we deduce the value of that variable. So to be 1, of that literal to be 1, otherwise we randomly guess the value of the next variable. So by using very similar, so we'll simplify the formula and we repeat it through, and we go through all the variables in this fashion, and we get an assignment in this fashion, and if S is satisfied in the process, we output the assignment. Okay. So the argument says, so this polytime algorithm produces a satisfying assignment with a probability at least, so 2 to the minus n plus the degree of isolation of x, the number of assignments which deviate in truth value from that of x, so over k for any satisfying solution. So when L of x equals n for an isolated solution, so we get a savings of n over k. So that's a satisfying assignment. So the proof is again very simple. So it follows from the previous kind of arguments. And so to get the particular savings, so we want 2 events to be satisfied. Okay, one is that that for sufficiently many critical clauses, or for sufficiently many critical clauses, the critical variable appears as the last among each set of variables according to the random permutation. Okay. So that event happens with a probability at least 1 in n, and given that happens, what is the probability? We set the other variables to correct values. And we set the other variables to correct values with the probability half. We don't have any other information, so therefore we get the total probability to be 2 to the minus n plus n over k.
Can you slow down to run through that again? Sorry.
Okay. So the algorithm kind of works the following way. So we take a random permutation, and
random permutation of the variable names.
A random permutation of the variables.
Okay.
And we look at the next variable in that order. So if there is a unit clause for that variable, we set the variable according to the unit clause.
So that's if that's the only way to keep satisfying that clause, you set that variable, make it true, so you didn't have to do any decisions, right. No random choice. That was forced. So you get these forced decisions essentially.
Right. So that's yeah. And for and if there is no unit clause for that variable, we simply guess its value with equal probability.
Okay. So then the next. Sorry.
Okay. So that's basically the assignment. If that process results in a satisfied formula, so then we output the assignment.
To be clear, this is the same thing as unit propagation. You just arrived at it from a theoretical perspective. Is that right?
Yeah, simplification by unit class. Yeah. So that's
and a random ordering heuristic.
Random ordering is
on the choice of next variable to pick.
Okay.
L of x, you said that's the degree of...
Degree of isolation, we generalized it. So let L of x denote the number of solutions which are false within Hamming distance 1. So that's the degree of isolation. Okay, when it's fully isolated, of course, L of x equals n.
And so can you just show the proof part?
Okay. So let's go through the proof slowly. Okay. So what is that we want? So we want a good permutation. A permutation is good provided that it will create n over k unit clauses. And when are we guaranteed to create a unit clause? So take a look at the unit clause. The critical variable appears as the last variable among the set of variables in that class. That probability is 1 in k, and we want, so the average number of such variables is n over k. A permutation is good when we can achieve that average number.
Okay. So this is an event over the choice of permutation.
Right. So the event E1 basically looks for good permutations, those permutations that achieve the average savings, and so you want to know what the probability is. And having achieved the average savings, then you want to set the remaining bits correctly. and each bit is set correctly with probability half. Okay, and so simple argument shows, so Markov inequality shows that that with probability 1 in n, so we do get a permutation that that achieves an average number of unit clauses, which is n over k or Lx over k. Okay. And the conditional probability is basically what is the probability of guessing the remaining bits correctly.
It seems strange that L of x appears positively in this formula. Like
This is the probability.
The more isolated the solution is, the easier it is to find. You would think that.
Right. So the probability will increase. The more isolated it is, so the probability will increase finding.
Is there some way to account for it? Because if the solution is not isolated, if there's like a lot of variables that could go either way and still it's a solution, it seems like that should also make it easier to find just because there's so much space in which it exists. Is there?
Right. So your intuition is right, and I will talk about it in a second. So if there are more solutions, so you are saying that that it should be easier to find, right.
But this is the probability of finding a particular solution rather than finding any solution.
So we can take the sum of the probabilities, and so that's going to be the total probability. That's where the savings will come. Okay. So yeah, this is important that so that we are focusing on the probability of outputting a particular solution. Okay, so that's the probability of success, and so let me so let's think more generally. So we are talking about a solution with a degree of isolation of L of x, and we have certain probability of success. But of course, in general, KCNF need not have isolated solutions, and so we're going to argue that that there is a combinatorial property here of any set of solutions that will help us in this regard. So let me simply define for each point in the Boolean cube, define this value. So for each point in the solution space of the KCNF, so let me define this this quantity called value of x, which is 2 to the minus n, so plus L of x. And it turns out the sum of the values over the set of satisfying solutions, assuming it's at least 1. So the formula that the size of s is at least 1, that the sum of the values is at least 1. A simple induction will prove that. Okay. So that means where the solution. So the idea is the following thing. So either there's at least one isolated solution, of course, in which case the value is high because of the degree of isolation, or there are many solutions which are not isolated. So then again, they all contribute small value. They all sum up to be at least 1. So now we can sum over. So that means when we have many solutions, okay, we can look at the probability of each solution being output and sum over all the probabilities. And due to that fact that we have, so that quantity will be, so that sum is exactly the same as before. So we can generalize it from isolated solution to a general KCNF. So there's more we can say to talk about the intuition that we have, what happens when you have many solutions. Okay. We can do a somewhat more detailed analysis to show that when you have many solutions, so the dimension essentially reduces. Of course, n is the size of the problem or the dimension of the problem. When you have s many solutions, so the dimension becomes n minus log s. Then you get savings on top of that. So that means if you can randomly guess, okay, if there are many solutions, you can randomly guess one, and then you are likely to be, that's likely to be a satisfying solution. And if you don't have many solutions, so then you have the isolated solution case. So that was the previous intuition. So now we're going to argue, so using an isoperimetric inequality, the worst way to organize points is in a subcube. So you pack all the points in a subcube. That's the worst possible scenario for this algorithm, and so that achieves that kind of lower bound. So that kind of upper bound in the satisfiability algorithm. Okay. So this is one of the unique properties of this PPZ algorithm. Many other algorithms don't necessarily share this property, so that as the solutions increase, so this algorithm gets better. So worst case is okay, when there's a unique solution. Okay. So that's the first part of the. So let me continue and complete. So let me take up the point that what happens when we have many critical clauses. Can we improve the algorithm? So we relied on the fact there is at least one critical clause for each variable at the satisfying solution, which is isolated. Okay. And there could be more than one. And in which case, so let's take the example. So let's assume that our satisfying solution is 1 to the n. That means the critical clauses will have the particular format. One variable will be positive, okay, one literal will appear positively, the remaining literals will appear negatively. Because for the critical clause to be minimal at that point, so it should be 1 followed by a bunch of zeros. So therefore, the critical clause will look like that. So, and so now we can make the following calculation. What is given a random permutation, what is the probability that x1 will appear as the last variable in the first clause or the second clause? So this probability is not 1 in 3. It is slightly better than 1 in 3. So it's 7/15 rather than 1 in 3. So we can get improvement over the PPZ algorithm, assuming that we have at least 2 critical clauses that have that kind of structure, or where the variables, but for x1, are distinct. But of course, in general, we cannot expect more than 1 critical clause. There's no guarantee that we have so that the formulas have more than 1 critical clause. And it turns out, so even then, so we can manufacture critical clauses by using resolution. Okay. So it may be that so let's look at the lucky situation we have. We have a critical clause for x1, and we have a critical clause for x2. Okay, we can resolve between the two to produce another clause, which is critical for x1. So we can manufacture additional critical clause for x1 by using resolution. And now if we compute the probability of appearing as the last variable in a random permutation for the first critical clause or the resolved one, the probability will be more than 1/3. So once again, we can improve. But again, there's no guarantee that we'll have such nice critical clauses that will help us resolve to get another critical clause. Okay. So for example, things may go bad. We may get unlucky. The critical clause for x2 might have x1 complement in it. Then we can't resolve them, so we got stuck. And this is in fact, and there's a reason. And the situation cannot be remedied, especially when we have a solution at distance 2 from x. So we have x, which is all ones. So flip the first 2 bits, so we get another assignment. Assume that assignment is also satisfying, so in which case we cannot hope to resolve and find a new critical clause. So to improve the algorithm, so what we are going to do is that we are going to look at we are first going to look at a special case. The special case is that de-isolated solutions. So that means a solution is not only isolated, but within distance 1, so there are no solutions. That's what isolation means. We look at distance d in terms of Hamming distance, and we stipulate there are no solutions. So such a solution is called de-isolated solution. So we assume de-isolated solution, and d is going to be sufficiently large. That's all we care about for our analysis, for our algorithm, and then we can now guarantee basically additional critical clauses through resolution. Okay, so let me give an example how this goes. So now let's look at an assignment that is at distance 2. Okay, since this is not a satisfying assignment, and once you plug that into the formula will become false. Okay. And so the critical clause for x1 still cannot be false because it has x1 or x2 complement. Since you flipped x1 as well as x2, that clause will still be true. But there must be some other clause that must have been falsified. So we take that falsified clause, resolve it with the critical clause for x1, and manufacture another critical clause for x1. And so we show that we can always do that. Because I'm only giving an example here. So if you think about it, we can always do that. And as long as we have a de-isolation. So for example, so there must be some clause like x1 or x2 or x4 complement to make that formula false at distance 2. Okay. And now we resolve C4 with the critical clause for x1, so to get this clause, to get another critical clause. So now we can use the previous argument and show that the forcing probability or finding the unit clause, the probability of finding a unit clause will improve upon 1 over 3, and that's good enough for us. So this is the intuition behind to go beyond PPZ and to get a small savings. Okay. So similarly, we can show that even if you were to flip the first bit and the second bit, even if you were to flip the second bit, we can get another critical clause. So with that intuition, so let me generalize the PPZ algorithm in the following way. So what we are essentially going to do is that we take the formula and we do an S-bounded resolution before we start the PPZ algorithm. Then we take a random permutation. Then we examine the bits in that order. And whenever we find a unit clause, we force that variable or we take that variable for free, and otherwise we guess the value. So same algorithm, except we do some pre-processing before we start. And the pre-processing is called S-bounded resolution. So that's the modified algorithm. We call it PPSZ, and to stand for the authors of the paper. And right. So let me talk about the analysis. So the analysis is a lot more complicated now. Okay, it's complicated, doubly complicated. First of all, even for a de-isolated case, so we have to go through more complicated calculations to figure out the average probability of forcing. Before, the average probability of forcing is simple. If all clauses have length k, a length bounded by k, the probability of forcing a variable that is making that variable appear as a unit clause under a random permutation is 1 in k, so that's simple. But then if you have clauses of critical clauses of varying length for the same variable, so you have to look at the so you have to look at the probability of that variable appearing as the last variable in the ordering for one of the critical clauses. So that's going to be a very messy calculation. We don't even know precisely what are going to be the critical clauses, and the resolution is going to produce them. And then we have to argue over the resolution, and the lengths will be varied, and there will be shared variables among critical clauses. Okay. Or they could be disjoint. Okay. So that requires a particular technique, and we introduce the notion of a critical clause tree to manage, to keep track of all the critical clauses we produce through resolution. Actually, not all of them. Actually, we keep track of a subset of them. And that critical clause tree is quite helpful in tracking the probability of forcing, and that's how we get the result for the de-isolation case. So that's the first set of difficulties. Then to extend the case to the general case ENF, it turned out to be kind of extremely hard. So we worked for several years, and we were able to extend the same result for K 5 or more. For 3 and 4, there was some gap. And thankfully, Timo Hartley came up with a much more a much nicer analysis and simpler analysis, and that takes the isolated case, de-isolated case to the general case, and with exactly the same bounds. Okay. So together we have a complete algorithm now for the general case ENF. So let me give you the intuition for the de-isolated case. Okay. So so basically, as I said, that we develop a tree that keeps track of the critical clauses generated, some of the critical clauses generated by resolution. Okay. So we keep flipping bits along each path. So that means we look at the next far away non-satisfying assignment. That implies some clause must be true, and we take advantage of that clause and resolve and then produce one more critical clause. So the critical clause tree basically is a tree labeled with variable, and the root is x1. So let's say we're talking about critical clause for x1, and along each path we have, so the variables are distinct, and the cuts of this tree correspond to critical clauses. So the cut is a cut. So we have a set of variables which acts as a cut. So you take x1 and then take the negations of these cut variables, and that defines the critical clause. So that's how we keep track of a subset of critical clauses, and then we can talk about the probability of a random permutation cutting this tree, or producing a cut for this tree. So through careful calculations, we could we were able to prove that the probability of outputting for any de-isolated solution, the probability of outputting is basically slightly better than 1 in k, and mu k. So mu k is basically limit of mu k is 1.644. So previously we had 1 in k for savings, and now we have 1.644 over k minus 1. Okay, that's a small improvement. So with that, so that also shows that this also shows that the number of de-isolated solutions is bounded by that quantity. And we can then use this to prove stronger lower bounds for depth 3 circuits, slightly stronger lower bounds, okay, where the product of the log of the fan-in times the bottom fan-in is strictly more than n. So you take an error-correcting code where the solutions are guaranteed to be isolated, and the bottom fan-in is k. So such a case ENF cannot accept more than so many solutions that are isolated from each other sufficiently well. And so we get a lower bound on the number of KCNFs required, and that can be generalized to deal with arbitrary depth 3 circuits, and that will give us a lower bound of 2 to the 1.282 times square root.
Question for problems that have only one solution, is that when the limit, is that when that limit is useful? You can use
the limit is as k goes to infinity.
Oh, as k goes to infinity.
Yeah. So for problems with only one solution, right? So there is no improvement. So the same bound applies.
But what about I guess as d goes to infinity, like.
Right. So one would expect as get more and more isolation, can we improve upon this? And we could not exploit that fact. So So we basically assume the critical class tree has distinct variables all out. So that's how we're able to to look at the extremal case, and then only we can analyze that. Okay. So let me do one more slide, and then we can stop. Okay. So for the general case, as I mentioned, so the analysis or the extension turned out to be much more complicated, and we had to use various ways of balancing various things, and we could only extend it for k greater than or equal to 5. But with a nicer and ingenious analysis, Timo has solved the problem after 10 years after the first publication. And he extended the result nicely for all k, and with a much simpler analysis. But the analysis builds on the unique case or the de-isolated case. So that's the basis, and kind of extending it to the general case. And also this algorithm is such that we could not extend it, we could not show improved bound of the same exponent when the number of solutions is larger. So in the case of PPZ, as the number of solutions is larger, so we get proportionate improvement. Okay. 2 to the n over the number of solutions to the power 1 minus 1 over k. So that's expression. So you would like similar kind of thing for PPSZ, but we could not prove that. And so you would like to preserve the exponent 1 minus mu k, 1 minus mu k over k minus 1, and have the base be 2 to the n over s. That we could not do. Okay. So there is some thinking that right.
So in the last, so that little o of one term was all based on the distance growing.
Right.
So in his arguments, does that little o of one term go away? It's just 2 to the n minus 1 over 1 minus mu k over k minus 1 would.
Right.
So that's the clean
Right.
bound.
Yeah, that's a clean bound. Yeah, that little o1 comes due to the distance. So if we take distance to...
And that's the best known for every k, or?
That's the best known for every k, but for k equals 3, TMO has a small improvement in a very small way. That's my understanding. I didn't fully go through the paper. If anyone remember, I believe it's in the 10th decimal or 7th decimal digit, there's a small improvement for a k equals 3. So that's basically the state of the art today, but for that improvement from TMO. Right. So that could not be, that was not extended to k equals 4 or 5. And
So actually, TMO had a slightly different algorithm, a modification of our algorithm that we were aware of. That he, instead of doing resolution in the first step and then just running the algorithm, he does resolution after each choice of variable. And this, in principle, you can get larger clauses because after you set certain variables, then possibly the clauses that you generate may be larger if you did it at the beginning. So this is an advantage. We are not able to use this, and he used this in his paper, but is this essential or for his analysis, or has anybody analyzed the original one?
it simplifies, I think his weight function, the way he balances various things. When you have too many solutions, there is some argument. So that's what we try to do. So we try to balance when you have too few solutions, so use some other argument, and when you have too many, use some other argument. So he balances them much more nicely, more elegantly. So that's the key. So that's the key to his result.
But is it essential that he uses this resolution at each step?
His proof, it looks like it's essential, but I didn't think of doing it otherwise.
Was any work done on the randomization of the PPSZ algorithm?
De-randomization? Yeah, so there are several results. I'm trying to see whether the constant is preserved. So the bound is 2 to the n times 1 minus 1 over k. I'm not sure if there is a de-randomization where the constant is preserved. So there are de-randomized. So there are deterministic algorithms of the type 2 to the n times 1 minus c over k. So 1 over k format is preserved. I'm not sure of the best constant.
So you can de-randomize PPZ using like KY independence or almost KY independence, right?
I do believe, Francis.
You can de-randomize PPZ like the random permutation thing by just using that KY as independence or something, or even almost KY independence. The problem is that this works for the unique set, but if you have general set, then okay, I was going to ask what goes wrong. Yes.
So we get a slightly larger constant there. Sorry, smaller constant, c over k. Yeah.
Smaller savings.
Yeah, smaller savings. I didn't follow the more recent results about de-randomization. PPSZ de-randomization is still an open question. Any other questions? Yeah.
So from the other side, are there lower bounds on KSAT based on, let's say, strong ETH? Like how far can you push the dependence on K?
So we'll talk about that. So, right. So there are some lower bounds. So if you look at the okay. So let me make the following definition. For each K, let sigma K be the best sigma K be the best constant for the exponent. So assuming ETH, we show that so the sequence of constants is increasing or non-decreasing. So that's a kind of lower bound. So that's what led to the strong ETH.
That doesn't actually answer the question asked, which I think is we should probably put on the open questions list, which is assuming strong ETH for any fixed K, can we argue that the constant has to be at least a certain quantity? And I don't see that, like if we came up with a 2 to the 0.001 algorithm for 3-sat, that would...
So that's one of the open questions in the third talk.
Oh, okay.
Right. So, right. So for example, significantly improving the constant, the savings from 1 in K to 1 in log K or log K will have implications for circuit lower bounds. So basically, all the known algorithms. So there's no attempt at. There's no success so far in improving the form of the solution, which is 1 in K savings. Other questions? Okay. Gather at 11. Is that right? Yeah, at 11. Okay.